Well, let me first share the slides for today. Basically, today we're going to start with a new chapter. And before we start with the new chapter, I'm just checking whether you guys have any question that you would like to ask regarding on last Tuesday's lesson. Any question? What we have learned last Tuesday is basically on concentration polarization. And then we have looked through also the other things regarding on mixed potential. So I hope the lesson that we have learned last Tuesday helped you a lot in answering your quiz. The quiz that I have gave to you last Tuesday is basically written on mixed potential. I saw some, I think, answers, but I guess it would be nice if you can actually make the drawings. I mean, you extend the line and then make a overlapping of this line, and after that, determine the E core and also I core. And the other things that you should also remember is that, yeah, Mahdi, how are you?
Yeah, I'm good. What about you?
Yes, good. I was explaining about the quiz last Tuesday. Okay, and then once you have like intercept the lines, you can determine what will be the E core value and also I core value. So before I forget, the E core, the I core value should be like anti-lock, because the axis that provided over there is actually log I. So you have to anti-lock the value, then you will get the I core value. So from the I core value, you can calculate the corrosion rate by using a formula. And I think with that, there should be no problem to answer your quiz. All right. So, any question regarding on the last Tuesday's lesson? Anything? Or perhaps later on, if you have any problems with your assignment 2, I think assignment 2, there's probably some parts that you will have some problems in answering that. But I believe if you haven't checked it, please check it, and maybe you can come back to me if you have any further question. Right. So for today, basically, we are going to start with a new chapter. Okay. This will be the last part of KAA 504, the first quarter. Okay. It will be mostly on the electrochemical corrosion monitoring and measurement techniques. So the last part, or the most essential part from the first quarter of KAA 504 is basically how to understand and how to extrapolate the data obtained from all these methods. So for corrosion, we have a few electrochemical techniques ranging from potentiodynamic polarization, linear polarization, electrochemical impedance, electrochemical noise, and also scanning electrochemical microscopy techniques. Probably we have seen, I think, a few examples in potentiodynamic, or especially the polarization methods. But further on, we will explain more details on what will be the types of curve that you will get and how actually you are going to discuss the results that you obtain later on. Okay, when we talk about corrosion measurement, it is actually related with corrosion monitoring. So when we talk about corrosion monitoring, it is also important to take note that this is one of the important things that we will consider in order to know whether the metal undergoes severe corrosion, mild corrosion, or less corrosion. Okay. So with the monitoring guided techniques, you can actually plan what you should do in order to protect your metals from corrosion or to reduce the corrosion process. Right. So some corrosion measurement techniques can be used online. Okay. constantly exposed to the process streams, while other provides offline measurements such as the determination in a laboratory analysis. Some techniques give a direct measure of metal loss or corrosion rate, while others are used to infer that a corrosion or corrosive environment may exist. So corrosion monitoring is the practice of measuring the corrosivity of process stream condition by the use of probes. So when we talk about probes over here, it means that the electrode that you will use during the monitoring, which are inserted into the process streams and which are continuously exposed to the process stream condition. Okay, so corrosion monitoring probes can be mechanical, electrical, or electrochemical devices. Corrosion monitoring techniques alone provide direct and online measurement of metal loss or corrosion rate in industrial process system. Okay, so we have a few varieties of corrosion measurement techniques. Things that you need to understand is that for all these techniques, we have a so-called non-destructive and also destructive techniques. Okay, so non-destructive, it means that it didn't destroy the sample. Okay, samples or metals are not destroyed. Okay. For example, we have ultrasonic testing because it's more or less surface analysis. Okay. Radiography is also another thing. Okay. Radiography will actually give you some information in terms of what will be the density, the area of your metal specimen or the samples. Thermography is also another thing. It just gives you, I think, what would be the temperature, okay, of or the surface temperature of your metals, eddy current or magnetic flux, as well as intelligent peaks. Right. So all these are basically known to be a surface analysis method. Okay. So we also have a corrosion monitoring techniques. Okay. For example, weight loss coupons. So in this case, the method is very simple. Okay, you just need to find what will be the difference of metals in terms of the mass before and after. Okay, a simple process where a metal is being inserted in a beaker or in a test tube. Then you put the electrolyte at the fixed dimension at a fixed time. Okay, you weigh the mass initially, and then after the process, you weigh the mass after, then you will get the mass loss. So this is actually known as weight loss coupon methods. Electrical resistance method actually measure the resistance of the metals. Linear polarization is also another technique that we have seen. It's actually measuring the overpotential to study the behavior of a current at the different overpotential values. Okay. Hydrogen penetration, okay, is basically also another technique to see how much amounts of reduction process have produced. Okay, so this is actually by measuring the volume of hydrogen produced. And then finally, we have galvanic and also potential measurement. All right, so we also have analytical methods by actually measuring the pH of the electrolyte. We also can use analytical methods to study or to quantify what would be the presence of dissolved gas, such as oxygen, carbon dioxide, H2S. This, of course, by the use of absorber or column. Okay. And then we can also use ionic chromatography. We can use ionic chromatography. We can use atomic adsorption spectroscopy. Okay, we can use also inductive coupled plasma to actually determine what will be the metal ion count. What will be ions or metal ions that present in the samples? You can actually use these methods, and also microbiological analysis to determine what will be the microbes present in the samples, whether it is a SRB types of bacteria, okay, or IRB, ion reducing bacteria. Okay. So other techniques will be on electrochemistry. This is the one that we will study in. We have the measurement, we have potential static measurement, potentiodynamic measurement, and also AC, alternating current impedance, or EIS, electrochemical impedance spectroscopy. So potential measurement, potential static, and also potentiodynamic measurement, all these are actually categorized as destructive, okay, measurement or testing. While EIS is actually categorized as one of the electrochemical methods which is non-destructive. Other things will be on the operational data, pH, flow rates, and also pressure and temperature. The most common techniques we use in industry are all these techniques. We have like weight loss measurement, potentiodynamic polarization, linear polarization resistance, electrochemical impedance, electrochemical noise, and also scanning techniques. So all these methods actually we will cover in this chapter. And the need for corrosion monitoring, as I said earlier, the need is actually to determine whether the materials or the metal actually experience severe corrosion, mild corrosion, or less corrosion. So with this indication, it can actually give you a prediction whether the metal can last longer or there's a time for replacement or maintenance. Corrosion monitoring techniques can help in several ways. First one, by providing an early warning that damage process condition exists which may result in a corrosion-induced failure. By studying the correlation of changes in process parameters and their effect on system corrosivity. By diagnosing a particular corrosion problem, identifying its cause and the rate, controlling parameters such as pressure, temperature, pH, flow rate, and etc. And also by evaluating the effectiveness of corrosion control or prevention techniques such as chemical inhibition and the determination of optimal applications. And finally, by providing management information relating to the maintenance requirement and ongoing condition of plant. The first technique that we are going to look at is actually known as weight loss method. Okay, so weight loss method is considered to be one of the simplest and also cheapest method. Okay, simple and also cheap. Okay, because in these methods you didn't need much things. Probably what you need is just a fixed metal specimen. Fixed means fixed size, okay, in terms of the size. You need just beaker or maybe test tube. Okay, then maybe you also need balance, the most important things. Because with balance, you can actually measure what will be the mass difference of your samples. And if you have timer or stopwatch, you can also use it to actually make it in constant. So the technique is actually very simple. You just need to put a known or a fixed area of plate into a container, and the container is actually determined, the volumes and everything. Okay. Volume is actually known, how many mLs. You can also have like the area, what will be the area in centimeter square, and the duration, the time is also known. Okay, so with all this information, okay, together with the initial mass, with initial, okay, and with final, you can actually do weight loss measurement. So that is why most of the industries, they actually use this as one of the first techniques, okay, to determine corrosion. The method involves exposing a specimen of materials, the coupons, to a process environment for a given duration, then removing the specimen for analysis. The basic measurement, which is determined from corrosion coupon, is weight loss. The weight loss is taken place over the period of exposure being expressed as a corrosion rate. So we actually have known how to calculate corrosion rate from, I think, chapter 3. And using the information resulted from this test, mass loss or weight loss, you can actually calculate corrosion rate. So what actually you can use? The outcomes that you can get from weight loss measurement. Okay. So you can actually get corrosion rate. Okay. Apart from that, okay, the metals can actually be analyzed, okay, using probably FTIR to see what would be the RAS phase, XRD. Okay. Can also perform SEM EDX, okay, scanning electron microscope to see the surface morphology, and EDX to determine what will be the elemental composition after, before and after corrosion. Okay, and even the solution, the electrolyte that after you have done it, you can actually see what will the pH, the ion content, and others. Okay, so this is actually the outcome. You can actually have a characterization, okay, of metals or electrolyte. Okay, and apart from that, it can also give you some indication. Okay, so this actually will be some advantages of weight loss techniques. Techniques is applicable to any environment. You can use different kinds of electrolyte, okay, either neutral, acidic, alkaline, and other things, gas, liquids, solvent, solid to particulate flow. And then it gives a visual inspection because you can see the color. You can see the color changes. When you dip the metals in the solution, you see that it becomes like brown in color. Okay. And then corrosion deposits can be observed and analyzed. As I said, this is actually with the guide of like XRD methods, SMEDX. Loss can be readily determined. Okay. And the corrosion rate can easily be calculated. So localized corrosion can also be identified and measured. And finally, the inhibitor performance can easily be accessed. So you can actually compare bare metals without any inhibitors in corrosive environment, and the other one, the other sets, you can add inhibitors and you can see what's the difference. But of course, this method has several disadvantages. Okay, so what do you think the disadvantages of the major disadvantages of weight loss measurement? Anyone wanted to guess? Jihad, you can. Oh. Mari, what do you think? What would be the disadvantages, the major disadvantages of this method?
The method of weight loss?
Yeah, for weight loss.
To see the... Do you mean that means what does it mean, or how?
No, the disadvantages. Disadvantage, because earlier I think I have discussed what would be the advantages of weight loss. It's easy to conduct, very low cost, cheap. It give, I think, a visual inspection and whatnot. What do you think about the disadvantages? Do you have any idea?
Mm,
Not sure.
not sure.
Mariam, what do you think?
Need to replace the metal.
Need to replace the metal. Okay. I guess I just take it as one point. The disadvantages first is actually it is a destructive.
Better to measure the thickness of the metal.
Thickness.
Yeah, because when you lose weight, that means the thickness will be reduced of the metal.
Yeah, so that is what I mentioned over here. The disadvantages of this method is actually it's destructive. It actually giving you some observation. A metal will be dissolved and what? So you cannot actually reuse the plate again. I mean, after this measurement. So first, okay, I think I take the point because Mariam said need to be replaced. Maybe if you want to repeat the experiment, maybe you cannot undergo the same sample again. You need to use or replace with another one because the process is actually destructive. What would be the other disadvantages? Anyone? I guess this is actually very much important, very much related. Diana, what do you think?
Environment in terms of temperature.
Okay, that's also another disadvantages, which is actually it has huge parameters, or how to say, high error. Because when you do weight loss, for example, you put the test specimen in a lab or maybe in other environment. So sometimes the condition can be like temperature 25 degrees. Sometimes it can be hotter than that. Sometimes it can be like lower than that. So there's no assurance. So there's a lot of errors in terms of the environmental errors that you can actually observe from these methods. So that is why I think the preferable methods when doing weight loss measurement is that you need to make it a few sets. Maybe for one sample, you make like 3 replicates or 3 samples at one time so that you will have the average values and also you can see what's the standard deviation values. Okay. Other things, Nazira, what do you think? Any idea, Nazira?
No.
No. Okay, the most important thing is actually it is time consuming. I think no one have ever talked about time. It is time consuming because in order to get the data, you have to wait for at least maybe you cannot do weight loss for 1 minute. You cannot do weight loss for 10 minutes. You cannot do weight loss for 30 minutes because it is still short and it is still requires more time to see the difference. Maybe you will need like 1 day, 2 days, 1 week, 1 month to see the difference. Okay? So it is considered as a time consuming method. Okay, unlike the other methods that we are going to learn after this on electrochemical techniques, that method is actually considered a fast method because it's you inducing current and the process is actually being accelerated. Because for weight loss, it is a naturally occurring process. Okay, naturally corroded. So you cannot see. I mean the difference within like a few minutes. So for naturally occurring process, it still need time to do it. Okay. In a typical monitoring program, the coupon are exposed for 90 days. So 90 days is actually equals to 3 months. Okay, quite long. Okay, duration being before being removed for laboratory analysis. But of course, this one is actually depend on the size, the thickness, and everything. Sometimes I think the recommended time would be like 1 week, 2 days, or something like that. Okay. This gives basic corrosion rate measurement at the frequency of 4 times per year. Okay. The weight loss resulting from any single coupon exposure yields the average value of the corrosion occurring at that exposure. So this actually have been taught before in chapter 3. Okay, you can actually calculate corrosion rate or the corrosion penetration rate, okay, by looking at the mass loss and using the different surface area, time, and other things. You can actually calculate corrosion rate. The coupons monitoring is the most useful in environments where corrosion rate do not significantly change over a long periods. However, they can provide a useful correlation with other techniques such as EIS, LPR, and other measures. So as I said, for these methods, even though the value that you will get is not going to be the same as the other techniques, but it can give an indication. For example, you are studying the effect of time, 1 day, 3 days, 5 days, 7 days, until 1 month. And then you compare it with electrochemical data, then you can actually, the value, as I said, is not the same because both techniques are not similar, but you can see the trend. The trend actually will show you almost the same trend. If you have like a different time, maybe you have a trend of increasing until certain time and then after that decreasing. So you will also the same things for the other methods as well. You can also calculate inhibition efficiency from weight loss methods. This is actually in the case of if you actually study the effect of inhibitor. So inhibition efficiency is calculated using this formula. Okay. So in this formula, IE is actually equals to W naught minus WI over W naught, where W naught is actually weight loss. Of blank. Blank means that no inhibitor. And then you have WI is actually a mass loss or the weight loss with sample, with CI, with corrosion inhibitor. Okay. So you can see this example, corrosion parameters of mild steel in aqueous solution in 1 normality hydrochloric acid in the absence and presence of different concentration of inhibitor from weight loss measurement at 35 degrees Celsius for 3 hours. You can see the weight loss is actually varying. For the blank, you will see the mass loss is actually higher. And when you add different concentration of inhibitor, what you can see is the mass loss is going to be reduced. Okay. And you can actually calculate the inhibition efficiency. For example, like for 1 ppm, okay, so the inhibition efficiency is calculated as follows. Okay, 241.5 minus with 23.1 over 241.5 times with 100. Then you will get the answer, which is actually equals to 90.43%. The rest is going to be the same thing, same calculation. 241.5 minus with 70.6 over 241.5. And for the corrosion rate, actually you can calculate based on the formula that you have seen earlier. Okay. So any questions so far for weight loss method? I guess this is the simplest method, the easiest one. Any questions so far from the floor?
No, Doctor.
Okay, so we are moving on to the next part, which is I think basically on electrochemical techniques. The first one is basically known as potentiodynamic polarization measurement. Okay, And this method actually have a standard, I think, reference, ASTM. So ASTM is actually stands for American Standard of Testing. So it's like, I think in Malaysia we have like MS. It's a Malaysian standard. Malaysia we have MS. For Japan they have JS, Japanese standards. British they have BS, British standard. For American they have ASTM. So we always, I mean, worldwide people are always follow either ASTM methods, British standards, and also Japanese standard. Okay. So for potentiodynamic polarization methods, we can actually categorize it as STM G5 or STM G61. Okay. So in these methods, it's actually using polarization methods. If you still remember, what does it mean by polarization? Polarization means that we are studying the behavior of current density at different overpotential values. Okay. This technique enables the electrochemist to determine information relating to corrosion rate, passivity, and pitting susceptibility. Okay, because during this process, what we are measuring is basically we are measuring current density, measuring I core. Okay, so when you get I core, you can get corrosion rate. Then for passivity, because of for the Teffer plot, you can see whether the metal will experience passivity, like for example this one, and then after that maybe forming a pitting. Okay. And then pitting, you can see, yeah, you have transpassive, and this is where pitting occurs. Okay. Potentiodynamic polarization is the characterization of metal specimen by its current to potential relationship. So this is why over here you will see that the plot is actually log I versus potential. When a metal specimen is immersed in corrosive medium, both reduction and oxidation process occurs on the surface. When a specimen is in contact with a corrosive liquid and the specimen is not connected to any instrument, it will be in service. In service, okay, the specimen assumes a potential which is relative to the reference electrode termed as corrosion potential. The specimen at E core has a both anodic and cathodic current present on the surface. However, the currents are exactly equal in magnitude, so there is no net current to be measured. The specimen is at equilibrium with the environment, even though it may be visibly corroding. E core can be defined as the potential at which the rate of oxidation is equal to the rate of reduction. So as what we have seen in chapter 4, we have actually know that E core actually resulted when you have an equal, okay, a forward reaction, which is actually oxidation, with the rate of reverse reaction, which is actually the reduction process. Okay, so in order to do this process or this measurement, okay, so what you need to do is actually you need to put in a cell. Okay, we have like maybe cell, and then you have your specimens with a fixed area serve as working electrodes. And this actually will be connected to a potentiostat. You have also a reference electrode, which is actually served to, anyone still remember what is the function of reference electrode? Nazira? What is the function of reference electrode?
Reference electrode to measure potential.
Yeah, correct. It's actually to measure potential. You have a potential stat here, and then maybe it goes to your PC. Yeah. Right. This is your electrolyte. In the cell, in the cell also you have counter electrodes. Shamira, what is the function of counter electrodes? If you still remember. What is the function of counter electrodes, Shamira? Sure, not sure. Hamda, what's the function of counter electrodes?
To measure the current, Doctor.
Okay, yeah. To measure the current, so you have one is actually measuring potential and the other one is measuring current. Okay. So after you have connected all these three electrodes into a potentiostat, okay, the first process that you will undergo is actually known as OCP. This is actually mentioned over here. Okay? OCP. So what is actually meant by OCP? OCP means open circuit potential. Before you start the experiment, when you put the metals together with the electrodes, the metal will immediately corrode. Okay, so that is why over here it is mentioned that the specimen is not connected to any instruments. Okay, it's not assuming it's not connected, okay, because it's not still recorded, but the process is already ongoing. So the aim of open circuit potential is basically to determine the stable state potential. Okay. For example, when you do OCP, you will have like a response between potential to time. So you see that when your metal is start to corrode, you start to give a behavior until it becomes stable. So as you see over here, okay, the potential response, okay, if your metal is actually iron, you will see that the stable potential will reach at certain time. Okay, so this may be equal to minus 0.4 volts. The time may be around 30 minutes or what. Okay, so you will use this as indication for the next sample. You need to actually do open circuit potential for 30 minutes because until then, the potential is considered to be stable. So why do we need a stable state potential? Okay, because if you remember, this technique is actually polarization technique. So with this value, okay, we will actually do polarization minus 0.4, okay, and then you will actually increase or decrease the potential value, neta A or neta C. So you will get a response of current, and you will get a response of current at cathode. So this actually will result you the so-called Teffer plot. Okay, all right. If the specimen is polarized slightly more positive than E-core, then the anodic current predominates at the expense of the cathodic current. As the specimen potential is driven further positive, the cathodic current component become negligible with respect to anodic component. So what does it mean over here? I guess what is mean over here is that when it is polarized more positive, if you still remember back in chapter 4, okay, this is where the applied potential is actually bigger than equilibrium potential. So equilibrium potential is basically the one that we obtain during open circuit potential. Okay, so when the applied potential is bigger than equilibrium potential, then the reverse reaction will be negligible. The reverse reaction will be the reduction process. You will have like more dominant oxidation process. Okay, a mathematical relationship exists which relates anodic and cathodic currents to the magnitudes of polarization. Obviously, if the specimen is polarized in a negative direction, okay, the current predominates, the cathodic current predominates the anodic components and become negligible. Okay, so for this case, you have like applied potential is lower than equilibrium potential. Then you have dominant reduction process. And is actually having more cathodic current density as compared to anodic current density. Right. So later on, you will see that the figure 1 shows the potential dynamic anodic polarization, plot of sample of 430 stainless steel. The logarithm of the current is plotted as the ordinate as a function of the applied potential. The potential dynamic polarization of the plot figure 1 can yield important information, such as the ability of the material to spontaneously passivate in the particular medium, the potential region over which the specimen remains passive, and the corrosion rate in the passive region. So this is basically the figure 1 that you will see. If, let's say that the materials undergo active process. Active means you have mostly linear. Linear at both process. Okay. So as I said earlier, for Tafel plot, you will have like one half is actually for anodic process. The other half is actually for cathodic process. Okay. So linear means you have like a formation of slopes for both sides. Passive means that you already have a limited current density, IL, limiting current density. As I said, limiting current density can form when you have certain things, like for example, the formation of passive layer. So passive layer actually comes from where? So passive layer is actually coming from the formation of metal oxide. Okay? All right. So in this case, you will see that at point A until B, AB, it is still considered as active process because you can see the slope is still like linear. It's still like you can find what will be the slopes and everything. This is actually considered as a active process. You still have an equal process of anodic and cathodic. At point C, okay, until it reach point C, what will happen is that a primary passivation potential. Okay, so the metal when it start to oxidize, Fe to become Fe2 plus 2 electrons, it will react with the other I think species. Like for example, you have like water with 4 electrons, and you have like what, 4OH2. Oops, 4H minus, sorry. Okay. Then it will actually react together to form the first rust product, which is ferrous oxide. Ferrous oxide. All right. So the ferrous oxide starts to form over here. Okay. You will see that FeOH2 start to form, and then it start to build up until it become stable. So when the surface is covered with the metal oxide or the passive layer, you will see that it actually resulted a so-called a limited current density. This one actually we have also studied in the previous chapter. Then the current doesn't give any changes or any response at all. You will see that there's a slight drop, yeah, because it is no longer active. Okay. Deactivation process. You will see there's less adsorption over here that occurs. Okay. Less adsorption of what? Adsorption of ions on the surface of electrodes. Then you have like saturation until it becomes passive. And then what happened is that at point E is passive region, and point F and point G is, this is where the transpassive region occurs. What does it mean by transpassive? Because if you notice over here, when the current density start to become constant and suddenly it goes up again. Okay, so what actually happened? Because earlier I told you, you have like Fe2 plus, and then when it start to like corrode, okay, then it will start to form Fe, OH2. Then you have a thickening of this layer until it become like immediately passive. Okay. So transpassive occurs when you have a damage of passive layer, maybe due to cracks, due to scratch, you have a failure, okay, at the passive layer, which actually promote water and oxygen to penetrate into this gap, into this crack, and actually produce a so-called pitting corrosion. This is actually what you have learned in chapter 3, regarding on pitting corrosion. So transpassive actually happens when you have a failure. This is where the failure of passive, then you start to have pitting corrosion. Okay, then this is actually why you will see that the current is actually increasing. But if there is no formation of passive, it is still active, then what you can observe is that it's still forming like active curve like that. Okay, any questions so far regarding on this one? Any question? Anything that you are not clear?
Victor, can you repeat the E states? What will happen in E?
Okay. As I mentioned earlier, okay, when you have the formation of rust, and you start to have the formation of rust, like ferrous oxide, hydroxide, and then it start to thickening, okay, and when it start to thicken, okay, it become like passive. Then you have a deactivation mode. You have like less adsorption, desorption, more desorption process, okay, of ions. And there's no more, I think, changes in current, which actually resulted so-called limited current density. Okay, so until then, okay, since the passive layer is actually made from metal oxides, so it still have a tendency to become cracked or maybe damaged, because this is actually a crystal structure, okay, a crystal rust. So it has these brittle properties. Okay. So when you have a brittle properties of a crystal, it can crack, it can actually fail. So that is why when it cracks, it is actually promoting oxygen and water to penetrate again. So now the corrosion actually occurs underneath the passive layer. So that is why suddenly you have a sudden increase in current density value, because there's an active process occurring again. Okay. So this is actually where the pitting happens. Okay. Any other question? Anything? I hope it's clear to everyone. So this is more or less what I have explained earlier. You have like a formation of ferrous hydroxide, okay, as the first layer, and then when it thickens, when it's further oxidized to form like magnetite or hematite, then you'll see that the thickness becoming thick, and this actually giving to the establishment of a passive layer. Okay. So in terms of the formation of rust, you will see that when the metal is actually undergo dissolution, start to form the first product. This is actually the clumps or the first product of rust. And then when you have like more clumps, it becomes like later with a layer, monolayer. And then after that, it's further oxidized to form like a more stable, like ferric oxide or hematite or magnetite. And then after that, when it thickens fully, so you will see that this is actually forming a passive layer. Right, so the outcome for potential dynamic polarization is, of course, a Tafel plot. Okay, so Tafel plot is actually produced when you polarize the potential from steady state potential. Okay, you actually polarize it anodically and cathodically at the value of plus minus 250 millivolts. Okay, so this is actually your core. And then when you polarize it more positively, this is actually positive 250 millivolts. And you polarize it negatively. This is actually the recommended values. I mean, plus minus 250 millivolts. I think later on when you do the practicals, you will understand it more. Okay, so some people use 250 and some also use like 300s, but not lower or higher than this value. Okay, so the information that you will get from Tafel plot is basically what? You can get E core, you can get I core, you can get beta A, you can get beta C, the Tafel slopes. Okay, and then from there also you can use like I core to calculate corrosion rate and others. Okay, so where is actually all this information? So as I said, E core you can get it easily from this point. Okay, so the I core, how about I core? You can actually get it from the tangent, the intersection of these two lines. Okay, I core is corrosion current density, E core is corrosion potential. Beta A and beta C, beta A is actually the slope of anodic, and beta C is actually the slope of cathodic. The corrosion rate can be calculated from here, because when you actually use the I core value, 0.13 multiplied with I core, multiply with equivalent weight over density, you'll get the value. And remember, the I core value must be in microamperes. Some patterns for Tafel plot. You can have a pattern where it's showing you the direction, okay, shifting anodically or cathodically. How fast? Okay, because in the measurement of potential dynamic polarization, you will set what will be the scanning rate. You have one parameter is known as scanning rate, scan rate. Okay. So if you actually have higher scanning rate, meaning that the process is actually higher. For example, if you use like 10 millivolt over second, it means that 1 point will be recorded every 10 millivolts. Okay. So if you use like 0.1, it means that 1 point it will be like measure for each 0.1 millivolt. Okay. So if you ask me which scanning rate is actually the best, okay, for potential dynamic polarization, actually the best value for scanning rate okay, for potential dynamic polarization will be around 0.25 or 0.5 millivolt over second. 1 millivolt over second is still acceptable, but it's still considered high. Because if you use a lower scanning rate, then you will have a more defined Tafel plot. I think the plot is formed nicer because each small points you have like measure it, then it will be like nicer. If you use like higher scanning rate, then what will happen is you cannot actually see the different much because the point is being recorded in the huge range. Okay. How far? This one is in the case of if you actually wanted to perform anodic or cathodic polarization. This actually with a specific reason, probably because of you want to see at which potential that your material will experience like passive and then pitting and whatnot. Problematic issues like this one is a combination of active and passive. Okay. You have like a cathodic active, and then you have like a limited current density for cathodic reaction. And then you have like ambiguous. This is actually more or less like a combination between like passive effect, scanning rate effect, and other things into your Tafel plot. So there's will be a variation, a different variation, but the shape is still the same. You have like a Y-shaped plot. And this is actually the examples of results you will get, okay, from potential dynamic polarization measurement. Data is actually being computerized. What you have learned in chapter 4 is basically the theory, how you can get the value. The value is actually calculated from Butler-Volmer equation. This is actually the function of Butler-Volmer because Butler-Volmer equation actually used to calculate I-core. I think these days all are computerized, so you just put the values, you just set the potential range, you just set the propellant weight, density, and area, it will calculate for you the corrosion rate even. Okay, so this one is a very old data recorded in July 1986. Liana dah lahir tak masa time tu?
Belum.
Belum. Jihad and Mahdi, you born this year? 1986? Mahdi? You are born?
No.
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 So, means that you still young. Actually, 1996 is the year that I born. So, but still, I'm still in my mother's tummy lah at this time because I was born in December 1986. So you can imagine how old this data is. Very old. And those days, I still remember when I did my master's with Prof. Jain. Prof. Jain was previously a professor in corrosion in USM. So he told me during 70s and early 80s, because he did his PhD in late 70s and 80s. All the data was recorded manually. He need to set the potential slowly. He increased one potential and then he recorded what would be the current value. So he just used, a manual extrapolation. He draw the Tafel plot manually and calculate it manually. So you can imagine how hard that time is. Now it's actually easier. So from this information, it gives you beta A, beta C, E-core, and this one, EI equals to 0. So this is actually known as open circuit potential values. The difference is actually not much. You will see that the best E-core value is that it didn't have much different with open circuit potential value. 0.47 with 0.50. So difference is just very small, 0.03 both. So yeah, I-core, you will get an I-core value and the corrosion rate. You can actually calculate or check your I think data whether the corrosion rate has been calculated correctly using the formula that we have learned in chapter 3. Okay. For example, over here, the value is given as 2.57 times 10 power of minus 3 amperes centimeter square. Okay, so if you want to convert it into microamperes, so what you need to do is you need to multiply it with 10 power of 6. Like in this case, 2.57 times 10 power of negative 3, you multiply with 10 power of 6. Oops. Okay, then you will get 0.57 times 10 power of 3. Okay, so the others, you just put the values as it is. This one is actually you obtain it from the equivalent weight, molecular weight over density, valency, 55.85 over valency of iron is equal to 2. Then you will get 27.93. This is actually the density of iron. So you will get values in MPY. And if you want to convert into MMPY, you have to multiply with a factor. So the factor for unit conversion that I said, in order for you guys to convert MPY to MMPY, okay, you need to multiply 0.0254. Okay, so please remember this value. Okay. Any questions so far regarding on potentiodynamic polarization? For this calculation, is it clear to you guys?
It's clear so far, Doctor.
All right. So I just want to show you if we have the effect of inhibitor. Okay. So how does this experiment happen? So as I said earlier, the setting will be like you have electrodes, you have like working electrodes, you have a reference electrode, you have a counter electrode connected together to a potentiostat. Is the electrolyte, and then it is being processed in PC. So imagine that the test solution 1, you put like blank, which means no corrosion inhibitor. And the second sample, you change the solution, blank plus with CI, with a different concentration. So what will be the behavior that you will observe? So when you record the data, okay, so imagine that for blank, you will get a plot like this, and with the presence of inhibitor, you will get a response like this. Okay, so can someone tell me what would be the difference that you can observe from this curve? What would be the observation that you can see from here if you actually overlay between a blank sample and also blank with the addition of corrosion inhibitors? Nazira? Nazira?
The overlapping, so we can count
The overlapping, we can count what? Not sure.
Not sure.
Okay. Who else? Maybe Mariam? What you can observe? I mean, just from here, from this curve, what you can actually see?
Not sure, Doctor.
Okay, I'll tell you. When you add the inhibitor, and I just give you an indication that it shows
Reduction?
like this. Sorry, what?
Is it reduction process? Is it reduction process?
What you can observe over here, first thing is that when you add inhibitor, the curve is actually below than the curve of blank. This is actually when you imagine you still use the same metals like my steel. Both is actually my steel, but the test solution, one is actually maybe this one is 0.5 molar HCl. This one is actually 0.5 molar HCl plus with Ci. Environment is still the same. You use acid, you use the same metal, my steel. But actually, when you overlay the data, you will see that the one that with inhibitor is actually producing a graph or plot lower than without the inhibitor. So what does this indicate?
The icon.
Yeah, correct. Huh? So this actually indicates that with the presence of corrosion inhibitor, UCI, it produces lower I core. So this is actually the I core for blank. Okay. And this is actually the I core for with the presence of inhibitor. So things that you still need to remember is that if you have lower I core, what does it indicate? Lower corrosion rate. Yeah. When you have lower corrosion rate, meaning that your inhibition efficiency will be higher. Okay. All right. So this is the first observation that you see. Okay. You see that the curve is actually, or the plot is actually lower than the blank. Second thing is you will notice that there's a shifting of eco. You see that the eco is actually shifted more positive. When you add the inhibitor, it shifted more positive. Okay. So what does this indicate? This actually indicates that there will be an inhibition process. Okay, so there's an inhibition process that occurs when you add the chemicals inside the electrolyte. Next, what will be the other observation? You will observe that, okay, the difference of current density between anodic, here is anodic, and here is cathodic. Which one is larger? Anodic side or cathodic side? Anodic side. So you have like beta A, mostly is actually related with the slope of your plot. This one, because you have like more difference in anodic side, so beta A is larger, which actually indicates that when you add the inhibitor, it actually inhibit or reduce the oxidation process. It still actually reduce or inhibit the reduction process, but the major inhibition actually occurs at anodic side. Is it clear to everyone? So that is why when you look at this effect of inhibitor, you have a different modes. Okay, you have like this one, a cathodic inhibition. Cathodic inhibitor. You can also have anodic inhibitor. You can have a mixed type. Okay, but predominant anodic. And this one is mixed type. Dominant and cathodic side. Okay. So cathodic inhibitor, it means that you didn't see much difference. For the anodic, you'll see that over here, no difference. Almost the same. It's almost overlap to each other. Meanwhile, over here, you will see that there's a tremendous difference in terms of cathodic current density. Over here, you will see that for cathodic current density, no difference. Not much difference, almost overlap. But I still see like there's some changes over here. Okay. And the major difference is actually for the reduction of anodic current density. So this characterized as anodic inhibitor. Mixed type, it means that both sides, okay, both anodic and cathodic experience reduction. Okay, but over here you will see it majorly at anode as compared to cathode. And while over here you will see that it is having more difference at cathodic or cathode as compared to anode. Okay. Any questions so far? Anything that you would like to ask? Right. So we can also calculate inhibition efficiency, okay, using potentiodynamic data. Okay. So what parameters that we need? Actually, we need I-core. This is actually the formula to calculate inhibition efficiency. I-core of blank minus with I-core of inhibitor over I-core of blank multiplied with 100. This PD, I just write PD if you calculate using PD methods. Oops. I-core of blank minus with I-core of sample divided by I-core of blank times with 100. If you have a higher percentage of inhibition, it means that it is effective. So here is actually the examples of potentiodynamic polarization data when you actually undergo corrosion inhibition. You'll see that the information provided is actually E-core values, beta A, beta C, I-core, and inhibition efficiencies. Okay. So the first sample is actually blank, which means 0 at 0 ppm or no concentration of inhibitor at all. Okay, and then you have a range of concentration 1 until 10. So over here, okay, you also been provided with E-core values, okay, and also beta A, beta C, and current density. You can actually calculate the inhibition efficiency at 1 ppm, for example, like this one. Okay, so I just show you how you can calculate. 754 minus with 131 over 754 multiplied with 100, then you will get 82.62. The rest will be the same thing. Okay. For example, like this one, you can calculate 754 minus with 110 divided by 754 multiplied with 100. You can answer. So the plot is actually not provided over here, but can someone tell me what will be the mode of inhibition? Anyone knows?
Cathodic, doctor,
Sorry?
is like a cathodic reduction.
How do you actually know that it is a cathodic inhibition?
Because the difference between the blank beta C is more than beta A.
Correct. This is actually a very good answer. even though the plot is actually not provided, but you can actually indicate the inhibition efficiency, I mean, the mode of inhibition based on the slope of beta A and beta C. So over here, you have like blank is 45 and also 193 for beta A and beta C. You can actually see the difference. Like this one, the difference is actually 2. This one maybe around 10. This one maybe around 9. And this one is around 3. Meanwhile, if you calculate the difference between this one, you'll see that it produces even bigger difference. Maybe this one is around 50, 58. This one is around 53. This one is 40. Oops. 37. And this one is around 20. So the difference is actually bigger as compared to this difference. So immediately that you know that, okay, is this still a mixed inhibition, or you think it's only cathodic inhibitor? What do you think? Jana, what do you think?
I think only cathodic.
Only cathodic.
Mm.
Okay. Actually, if you still have like a difference, like for example, if the difference is not too much, like 2, 1, or 3, we can say that it's just cathodic. But one of the concentration is actually giving slightly bigger, maybe 10, 9. So we still can consider this as mixed, right? But dominant, predominantly cathodic inhibition. Okay, is it clear to everyone? So this is also another example. This one is memory for me. This example is actually taken during my master's study using Gambir, Unkarya Gambir. I did my master's in the year 2008 until 2010. So this is actually the data that I got, I mean, long time ago. Okay. So I use a different solvent extraction, ethanol, for example, ethanol extract, and I perform potentiodynamic polarization. So we have this data, E core, we have I core, beta A, beta C, okay, and you will see the results as it is, right? So the inhibition efficiency can be calculated as follows. Okay, you can actually calculate, for example, like this one. You can calculate the inhibition efficiency of here 237.6 minus OA 39.2 divided by 237.6, okay, multiplied with 100. Then you will get the value. Okay. So the mode of inhibition, okay, so you can see that the mode of inhibition is mixed type because you have like still both sides have a difference, but predominantly at cathodic side. In fact, if you calculate the difference, you see more difference is actually obtained at cathode, right? And you can also perform surface analysis after you have done with the potential dynamic polarization. As I said, potential dynamic polarization is a destructive method. Okay, when you do the measurement, okay, it will corrode the sample, and you can actually analyze it. You can actually take the samples, the specimen after potential dynamic polarization. You send it to SEM analysis, and you will see a fresh mild steel without any treatment. It's very smooth. Okay, and when you treat with acid from very rough, okay, rough surface, and then with the addition of inhibitor, you will see that it's slightly smooth. It's almost comparable between the fresh metals. Okay. just a few slides before we end the lesson for today. This is basically the other things that we can do for potentiodynamic polarization. The method is actually known as cyclic polarization methods. It's not like a cyclic voltammetry. So in this case, the aim of cyclic polarization is actually to determine pitting corrosion. It can be used to determine pitting corrosion. Okay, all right. So how does this process actually happen? Okay, so when you do a normal polarization or potentiodynamic polarization, you will get something like this, right? Okay. In cyclic polarization, you actually increase the anodic polarization, or you increase the anodic overpotential. Maybe it's no longer 250, but maybe 500 millivolts or even more. So what will happen is actually you will have more data, okay, more current, more anodic current response. So over here you can actually observe, okay, passive, transpassive, and then after that, until certain point, it will reverse. Okay, and actually form almost like a second, I think, Y shape over here. So as we know earlier that when actually you increase the potential more positive, you can see at which time or at which potential does the metal become passive. Okay, because you already know that this is where you have like a passive region. And then there's also the region where you actually experience transpassive. Okay. So when you have a transpassive, okay, over here, then this is actually your E pit, or so-called pitting potential. As mentioned over here, you have like passive here, and then this is the region where you have transpassive, and start to goes up. Okay. So when it goes up, this is actually known as hysteresis loop. It forms like hysteresis. I guess maybe if you learn 507 on adsorption isotherm, you have a hysteresis, adsorption and desorption. It's almost the same concept. You have like adsorb and then after that dissolve. All right. So the other things that you have to remember is if you have a bigger hysteresis loop, means that you have more or a lot of pitting. Okay. People are actually looking at the area of the hysteresis loop. If the area is bigger, then it means that the material actually produce a lot of pitting. Okay. So there's also another thing that you can observe over here. This is actually known as ERP. Okay, this one. What is ERP? Over here, it is mentioned as EPRO. ERP is repassivation potential. As I mentioned earlier, pitting actually happens when you have a failure of passive layer. You have a failure, you have a crack. Water and oxygen can penetrate and it forms pitting. So when you have a pit, then this is where you have a response of transpassive. Okay. And repassivation actually happens when there's a passive layer forming at inside your pit. Okay. Repassivation means that the formation of second passive layer. And the second passive layer actually forms at pitted metals. Okay. It's already formed pits, and then when it's becomes stable, it's already forming another passive layer inside the pit. Okay. So this is actually ERP. Anything that, I mean, after it reverse, and it overlap back to the point, this one, the intersection point, this call it ERP. Another thing that you can actually get is actually this one is known as reverse potential, EREV, reverse potential. Okay, and this one at this point, okay, over here, okay, it is known to be I pit. Okay, pitting current density, okay, over here. The rest you get the same thing lah. I mean, like this one is I core, okay? This one is eco. All right. So this is actually to show you the examples of pitting corrosion. If you have metals, okay, when it start to active and then form passive, and then this is actually the pitting potential, transpassive, reverse potential, and this is actually the repassivation potential. All right. So what would be the indication if you have like two samples, okay, that you perform cyclic polarization? Two samples that you actually add inhibitor, the other one without inhibitor. Okay, maybe with inhibitor you will notice that it will be like this. Okay, so without inhibitor and also with inhibitor, what you can actually see is that, of course, this is the I-core for blank, and this is I-core for sample. You have also this one is EPIT, pitting potential for sample without inhibitor, and this is EPIT with inhibitor. Okay. Hysteresis loop, you can observe that the hysteresis loop for blank is bigger as compared to with presence of inhibitor, low hysteresis. So low hysteresis, what does it mean? Low pitting. And then this is actually the ERP, repassivation potential for without inhibitor. and this is actually the ERP for with the presence of inhibitor. Okay, so you can actually discuss. I mean, like this one, you can see that ICO of no CI is higher. Okay, and then what else? You can also observe that more hysteresis for without inhibitor. Okay, and then you can also see that the eco shifted anodically when you add CI. Okay, you can see that this eco it is shifted more positively, right? So, okay, any questions so far for cyclic polarization? Anything you didn't understand about
What is I beating?
IPting?
Yeah.
Okay. If you look, I mean, if you look from this drawing, maybe it's hard for me. It's already crowded. Okay, so this is actually the plot for this one. You see active, and then goes up. Okay, before it returns. So this one is actually known to be EP, and this is actually your IP. Okay, Madi?
Okay.
Where you get your EP, this one is actually over here is equal to IP. Okay?
Okay, doctor. Thank you.
Any other question? Anything? Anything that you didn't understand? Hamda,
Doctor, I
is it
have
okay for you? Yeah, Madi.
Doctor, I have a question about the previous lecture.
Previous lecture? Previous slide or previous lecture?
Previous lecture.
Oh, previous lecture. Okay, but before that, any other question for this one? For cyclic polarization? Anything that you want to ask? Nazira, okay ke?
Okay, Doctor.
Okay, all right. So maybe I just like yeah, for this, maybe we'll continue next week, I guess. Any other things? If no, then maybe yes, Madi, you can proceed with the question.
Doctor, the last question in the slide 4, I couldn't get the same when we calculation. I couldn't get the same answer, the same number.
Is it from this slide or from
No, previous slides, previous notes, not in this, in the previous lecture, previous class.
okay, previous class? Slide number?
Number 4.
Okay, let me open first the slides. Number 4. Wait, I should share. Is this one, Mahdi? Is it this one?
The last slide, Doctor, yes.
This one?
No, the last page. And page.
This one?
The last example, page 60.
60. This one?
Yeah.
Okay. Which one? Which question?
Question A.
Okay. This one? Yes. To calculate this rate.
I could get, yeah. I couldn't get the same answer, minus 6.055.
Oh, this one?
Yes. Yeah. I get only minus 5.
Minus 5.
Yeah, minus. Oh, no, minus 0.2.
Minus 0.2. Okay.
Yeah, 0.2.
Anyone have tried to calculate this?
Doktor dah cuba juga tapi dapat berbeza juga daripada tu. Negatif 8.33.
Negative 8.33.
33.
Saya dapat sama
Saya dapat sama dengan Liana juga.
Negative 8 point something. All right. Wait. So first thing to look at is that what would be the potential value that you put. I think the potential value provided over there is for nickel and also for hydrogen, right? So did you actually put the value as it is or what?
Yes, for another it's minus 0.25.
Okay. That we try together. Okay. So the information provided over here, I think I should jot it down. Minus 0.25. Can someone help me to read the value? What would be the potential value for nickel? Minus 0.25, right?
Yeah, minus 0. Yes, right.
0 volt. And then anodic current density, what's the value?
Anodic is 1 plus 10 power minus 8.
Okay, and then cathodic current. 1 times 10 power of 8, right?
Minus 8.
Minus 8. Okay, and then for cathodic?
For cathodic 6 multiplying 10 power minus 7.
Minus 7.
Yes.
Okay. Beta A?
Beta A is 0.12.
Beta C minus
minus 0.1.
0.1. Okay, all right.
Yeah.
So if you want to use this formula, first thing is, if you notice over here, this is actually the anodic potential. So if I take this formula to calculate log I, is equals to 0.25, not negative. It should be positive because it's already in anodic. So we just convert it, reverse the value to become positive, minus 0, okay, plus with 0.12 multiply with log I A, which is 1 times 10 power of minus 8, minus with minus 0.1 multiply with 6 times 10 power of 7 divided by 0.12 minus with minus 0.1. Can you try?
Yeah, I'm calculating now, doctor.
Actually, it is just the difference. I mean, that's why I asked you to try, because if you try, maybe you know, oh, I should consider the positive sign, negative sign. I should reverse it or not. What do you get? You get the same answer?
I'm still doing it.
Yana dapat, Yana?
Tengah buat.
Okay. Okay? Oh, not yet.
Not done. I got 0.25.
0.25?
Maybe I did wrong, something wrong.
Saya dapat 1.136, doktor.
1.136 pula dah. Tak dapat negatif ni.
Tak. Sekira 2 kali dapat 1.136.
Oh, my mistake. Log. Saya terlupa. I forgot about the log things here. Try again. Just log first and then multiply.
Dapat.
Dapat? Oh, siapa tu? Nazira. Oh, dapat lah.
Dapat.
Dapat, doktor.
Dapat eh? Okay. Liana, dapat? I'm truly sorry, but I forgot about the log thing.
Kejap.
So should log it first. So got it, nah? And then when you anti-log, minus 6.055, you will get the answer 8.8 times 10 power of minus 7. Okay? Okay, Madi?
Okay, doctor. Thank you so much.
Yeah, I hope you guys can get it. This is actually the difference. The clear difference is that over here, it should be positive. Huh?
Yeah, okay, doctor.
Yeah. and the values of beta A and beta C, you still remain the symbol. Even this one is still like negative. This one is still like negative.
Only the potential for
Anode, for anode should be
yeah,
positive.
that is should be positive. Thank you so much, Doctor.
Okay, any other question? All right, so if no further question, then I guess, wow, I got, I think a chat over here. I didn't saw it. Okay. Oh, it was Jihad who replied. So I'm very sorry. I just noticed your chat, Jihad. Okay. So I think if no further question, we shall continue next week for linear polarization resistant methods. Once again, if you have any problems regarding on your assignment 2, please let me know. We can like discuss it in the group or what. So if no other question, then we'll adjourn the class today. Thank you very much for your kind attention and hope to see you next week, Tuesday. With that, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Doctor. Have a nice
Thank you, Doctor.
weekend.
Thank you, Doctor.
You're welcome.
Thank you so much, Doctor.
You're welcome.